Professor Reddy, for first of all, I appreciate your energy in organizing these webinars, which requires a lot of effort. Even for the last 1 week, he has been reminding me about this talk today. And when I said about the title of my presentation would be Uncharacteristic Swell in Soils, he very much appreciated. Actually, I thought he'll suggest some changes, but he accepted the title and said it would be very interesting. Coming back to myself, Professor Reddy has introduced me, but I will tell you, I am all farmer. And what I will be next, I don't know myself. And now my inspiration is, next slide. Professor C. Radhakrishna Rao, who received a prize equivalent to that of a Nobel Prize in statistics at the age of 102, that is this year, has been awarded. But as all of you know, in India, once you retire, you are written off. But I admire the energy of Professor Radhakrishna Rao, who has continued his work. After retirement from India, he went to US and pursued his interest in statistics, became professor, and also this year he just got a prize which is equivalent to that of Nobel Prize. But I don't think everybody can do that. Everybody is capable of doing, but many may not get that kind of opportunity. Coming back to myself, I think if I have to go like Professor Radhakrishna Rao, I should learn from failures. I'm not talking about failures from IN, I'm talking about failures in foundations. Next. See, foundation failures are not very uncommon, but they are not desired. And many times we attribute failures only to movements such as uniform settlement or heave, uniform horizontal displacement, extension or compression, differential horizontal displacement and settlement. In many cases, this failure may be reflected not the collapse of the structure, it may reflect as distortion, also affect partitions, ceilings, floors, and roofs, etc. And see, this is a common. When you say keep, this is when you load a foundation beyond its desired capacity or allowable pressure, it will undergo settlement or develop cracks and fail. This is the one which all geotechnical engineers are well aware of. Next slide. Now, this, as I told, the failures may be as reflected in structural cracks, foundation movement, opening distortion, foundation movement, tend to distort openings and often cause doors and windows to stick. Floor movement, the initial effect of foundation movement and unstable soil beneath or bulging of the floor. Bulging. Today we discuss about not necessarily due to all problems related to heavier load or soil capacity, but unexpected, unseen, surprising heaving, whose characteristic behavior is totally different from the heaving we know from geotechnical engineering. Next. For that, soils are initially classified as coarse grained soils and fine grained soils. As all of you know, there is not much of a problem in foundations and coarse grained soil, but when it comes to the fine grained soil, we have to be lot more careful, because each clay behavior is quite different from each other. Coming back to behavior of fine grained soil, See, why different clay soils or fine-grained soils behave differently? It is because they undergo more volume changes. They swell and sink on wetting and drying, and also they are influenced by ionic concentration or the composition of the pore fluid or the leachate or any other contaminant that is present in the leachate. And how this reaction under different environmental conditions depends on the way they are formed. Whether all of you know how different clay minerals are formed. I just summarize, but I will not go into details of this, as most of the geotechnical engineers are well aware of how different minerals are formed. But their properties I can briefly summarize. As you know, clays are formed when the rocks are in contact with water, air, or steam. Clays are formed either at or near the surface of the earth. So depending upon the way carbonic acid is there in acidic condition or different rock types like feldspar they undergo, leading to the formation of different types of clay minerals. Again, I'm not going to spend too much time on how clay minerals are formed or how clay minerals behave in different environment. Next slide. See, these are the various common clay minerals, including kyanite, halloysite, pyrophyllite, smectite, vermiculite, illite, chlorite, and mixed layer. See, today I may cover little bit about this mixture layer mineral, where not much data is there, how they behave, particularly in a environment which is not just normal pore fluid is water, but when it is contaminated with any chemicals, etc. And kyanite is considered as relatively non-expansive, and illite is somewhat expansive, and chloride mineral along with illite is very common, and it behaves slightly different. Vermiculite is ability to absorb water, but not again and again. You know much about smectite, particularly when you come to the topic of smectite minerals. It is extremely different. Say, for example, I can say sodium montmorillonite. All of you know it. The liquid limit of sodium montmorillonite can go up to 1,000. Whereas calcium montmorillonite, it can be only less than 200. You can estimate the way the spectate behave just because of change in the exchangeable ion. So when that is the case, so lot of changes in the behavior, particularly the swelling behavior of montmorillonite can vary very drastically, because the amount of water that is absorbed, but sodium montmorillonite or sodium secnite is 18 layers of water molecules are there between layers, whereas calcium, it can be very, very less than that of sodium smectite or sodium montmorillonite. So this is the normally changes in occur in the clay mineral. Say for example, initially when it is a sodium montmorillonite, and when it is exchanged in the field condition, the swelling pressure or the allowable pressure can change drastically, and there can be lot of implications of the structures that are built on this kind of soils containing montmorillonite. So this is actually, of course, very well known to not all geotechnical engineers. At least I see 50 to 60% of geotechnical engineers know the change in the behavior of montmorillonite with the change in the environment. Whereas it is very little in the case of kyanite and somewhat in between in case of light. So the changes in the properties or the behavior of clay soils can affect the behavior and the performance of the foundations that are constructed on this kind of clays. So now I will talk about little bit about interstratification of phyllosilicates. These are not like a well-defined minerals like a kyanite and smectite. These extreme minerals can be interstratified by different layers of each layer varying from one to the other. You can say for example, there can be light and then can be smectite, then light, and there is the extent of randomness of these layers. All these layers, clays are phyllosilicate layered structures. Very well the layers of smectite and kyanite and light. And when it is an interstratified mineral, the structure can be quite complex. Next slide. So basically the clay minerals behavior depends on the cationic change capacity. I think I hope all the geotechnical or foundation engineers well aware of the cationic change capacity, specific surface area, and the dominant clay minerals present in the fine-grained soils. So the clay minerals can have very high swelling if it contains 1:1 whose specific surface can be up to 800 meters square per gram. So specific surface has a great role when it comes to the changes in the nature of the fluid or nature of the chemical that is going to interact. Whereas, say, for example, kyanite can be only 10 or 20 meters square per gram. So when there is a huge change in the cationic change capacity, as I told, liquid limit of montmorillonite can normally, even if it is a natural condition, not highly purified, it can be 300, 250, etc. And again, it can change depending upon exchangeable ion. And the interaction that takes place because of the large specific surface of these clay minerals. So without much going into details into this aspect, which I assume that most of the geotechnical engineers have some idea about this, but the topic I wanted to cover is slightly different. This is only some basic I'm trying to give for that. See, this is a summary where the cationic change capacity and swelling potential of different clay minerals can change. Next slide. Now you know the clays, particularly when they have negative charges on the surface, no particle which is not ionically balanced can be stable. These negative charges on clays are they're neutralized by attracting the positive cations, whether it is a sodium or calcium or any other ion. But when these clays which have got cationic change capacity, when they also allow water to be absorbed on these clays, and the particles are separated in the initial stages of swelling. I am trying to explain the basic swelling as understood today by almost all geotechnical engineers. The first stage of swelling can be separate the particles by 2 nanometers, and the second stage will start beyond 2 nanometers, and there will be steep swelling with the amount of water available, and the swelling continues if the cations are present, because cations also they have hydration number, they will try to take ions. In the process, the sheet structures are separated to the extent depending on the amount of water that it can take. And of course, once the amount of absorbed water is completely satisfied, then the third stage of swelling continues, where the sheets are separated only to a small extent, And normally in this stage, there can be some kind of flocculation. I'm assume that all of us are very familiar with the effect of changes in the fabric, whether it is dispersed or flocculated. The behavior of clays can change very much depending upon whether it is flocculated or dispersed. Next. This is again, see how the negative charges behave once they are absorbed on the clay mineral surface. We will try to explain the extent of separation by diffuse double layer thickness. See this, the clay mineral surface, when negatively charged, the positive ions are trying to come as close to as possible. The closest layer of positive ions, they are in the stern layer. They are much more strongly absorbed to clay mineral surface. When it comes to next stage, the attraction goes on decreasing. So how the concentration of anions and cations are distributed near clay mineral surface, that dictates how the clays can swell and consequently how these clays can behave in contact with water. See, there is a theory, Chapman theory, which you can calculate the thickness of diffuse double layer. That means the extent the negative charges of clay minerals can exert its role or control over water as well as the cations that are absorbed on the surface. So this is used, but it is very commonly used, most theoretically, but in a field condition, there are a lot of limitations. I will tell you that next. Limited, because diffuse double layer theory can somehow account to some extent on the behavior of smectite or martelonite kind of clays, but it cannot explain the role of cations on the kinetic type of soils. This is where most of the predictions based on the liquid limit of the soil, they are only relevant to the spectate type of minerals. So when it comes to the kinetic soil and the changes, it totally fails. In fact, I've seen, I should not name some of my farmer students, not my student, I'm talking about the whole group, where they conveniently eliminated the kinetic soils in their prediction and confined themselves to soils which has got montmorillonitic type. And again, these predictions can go wrong when there is electrolyte concentration or sometimes when there is hydroxide. Say for example, in case of a kyanite, when it comes to like minerals like ions like hydroxide or DMF or dimethyl sulfoxide, then it can throw away hydroxyl ion of the kyanite and it will swell. In fact, these clays swell much more than montmorillonite in case of certain ionic concentration present in the leachate. Sorry, I would like to repeat this. Kyanitic clays, because of replacement of hydroxide on its surface by other ions like fluoride, DMF or DMSO, can swell much more than montmorillonitic soil. So it has got a lot of implications in prediction of its swelling behavior in the presence of certain concentrations of some ions or fluids, whose dielectric constant also comes in the picture. That's why one school of thought is that the behavior of kyanite cannot be explained by the same standards of theories that are applicable to montmorillonitic type of soils. So there is a lot of problem when it comes to explanation of kyanitic soil, which can sell more than a montmorillonitic soil. That's why we say, for example, we can predict the percentage of swell, odometer or pre-swell odometer swell at a nominal surcharge. Depending upon the, of course, density plays very important role. Different clay minerals swell to different extent. And this is the, when you plot time versus percent swell, the characteristic swell behavior is occurred, initial, primary, and secondary. And we say coefficient of secondary compression, the secondary swell, you can say, similar to what you can say about compression. So, but in the forefathers of soil mechanics, they never try to probe too much into the swelling. They concentrated only on the settlement or compression that can take place, unlike the case of swelling, which can be similarly, you can classify the swelling. And predictions are based on the nature of the curve. Based on the initial way the soil can swell, the ultimate swelling is predicted based on the mathematical nature of this curve. That is S curve. We can predict the ultimate swell. Of course, that is a separate topic. Maybe the question and answer we can discuss about that. But we can predict the swell behavior of normal soils based on the swelling in the initial stages of swelling. Then another factor, as I told, is the fabric. The fabric is a very important thing. In fact, I used to ask my students, when I ask you in the middle of the night, and what is a flocculation, what is a dispersion, you should be able to change. And when the structure of the foundation soil changes from flocculation to dispersion or dispersed to flocculation, depending upon the environment. Say, for example, when the salt concentration in the fluid is very high, there will be aggregation. When the pH is very high, the soils can swell very high, and there will be huge difference. So again, today, still I am covering only the conventional aspects. Now I have to go to quickly switch on to my focus to unconventional, uncharacteristic cell. What I am telling, the swelling types of soils are clays, and the nature of its swelling and the prediction of their swelling, how it can change with the ionic concentration, and how it can change with the chemicals that are present in the system, all can be predicted, understood, can be taken care in the design of your foundations based on the soil behavior characteristics. Now, this is the beginning of my actual lecture. This is only introduction. Don't be afraid. I will not take more than what Professor Reddy has allotted to me. And I will talk briefly about the behavior of the soils without and with the chemicals. When there is a cationic change takes place, there will be change in the behavior. When the dielectric constant of the poor fluid changes, we can explain the behavior. When the anions are present in the system, the characteristic swell of the soils also can be understood. These changes, to some extent, are understood, but still people have not concentrated when, or this can be explained why these changes in the characteristic of soils can occur. So these changes will, swell potential can change depending upon the type of clay, type of exchangeable ions, electrolyte concentration, particle size distribution. More than particle size distribution, I will weigh much more to void size distribution. See, same void ratio, if it is divided into finer voids of large number, total void ratio being the same, the void size matters a lot. Say, at the same void race, when the void sizes decrease, the tortuosity comes into the picture. the way the fluid can go through the small voids, finding it very tortuous, very difficult to go through the soils when the voids are divided into very, very finer sizes. And of course, total water content and the behavior. Suppose the soils are loaded more than its allowable swelling pressure, then the variations are very, very minimal. Whereas if it is underloaded, the problems are much more. Say, for example, schematically I put, when there is a contaminant fluid beneath the foundation, contaminant is occurring. When the contaminant is trying to enter into the pore fluid, there is high concentration of salt, say for example. Of course, these pictures I can go on putting many scenarios, but normal, most simplest way of expressing is when the contaminant is flowing, the swelling pressure of these soils can reduce and the settlements will be more. So it will not go through uniformly at a time. So the structure will tend to settle towards it. And vice versa. If you put the contaminant which can cause swelling, the structure will undergo different kind of tilting. So if you dance, well, it's okay. We don't want the structures built on our clays should dance. Dancing when you appreciate on a movie or yourself, but when the structure undergoes settlements on one side uneven, and unlike in the case of settlements, heaving also can cause, and differential heaving. Normally, people are not talking about differential heaving as much as we talk about differential settlement. So I would like to emphasize more on differential heave in this kind of scenario rather than differential settlement. So swelling behavior. Yeah, again, one more example. The kynetic soil can swell much more in kerosene, whose dielectric constant is very low than in water. Whereas your montmorillonite soil can swell much more in water, but when it is a kerosene. If you take kerosene as the pore fluid, which soil will more call it swelling type? You call kyanite as a swelling type and montmorillonite as non-swelling. That's why the whole basic concept of expressing free swell index is modified. We should not take these volumes as real, and to define that we have to modify this equation V minus Vs by Vs. The Vs is the volume of the soil solids, total volume in kerosene or water. Likewise, so because of this kind of scenario, there can be lot of distortion to our understanding of relationship between liquid limit and plasticity index. Again, for want of time, I'm not going into details. And then we have understanding that a plastic limit is higher than sinkage limit. No, or not always. So both in cases, normally what do we say? When the liquid limit increases, sinkage limit decreases. But there are cases where liquid limit and sinkage limit both can increase. That is because of the pore fluid concentration varying or contaminant present in the fluids. And similarly, density effect on the strength of the soil. As we know, as the density decreases, dense decreases. But in some cases, when the density is decreasing, strength also is increasing. And this is the normal scenario where some of the changes are, when the soils are flocculated or connected, density is much less important than the structure. So there can be a scenario with increasing density, strength can decrease. If we say that, people won't accept immediately. But there are conditions where density increase is not necessarily increase the strength if the pore fluid is different. And coming back to lime stabilization, I just now understood that still some people are actively working on stabilization of expansive soil, because when these, I know, now we know why we have to stabilize monto-malonite, where conventional mechanical stabilization is not that effective, but lime stabilization can bind the soil particles, and I'm not going to explain the basics of soil stabilization using lime. Lime can produce cementitious compounds which can bind the particles, but the density decreases. This is again I emphasize. When the soils are flocculated initially and they are bounded or cemented by cementitious compound, the density decreases. The volume initially appears to be increasing, little increase, but the strength is very high. And this is the case where lime stabilization can distort. When I ask some people, some students in many institutions, when I add lime, what will happen to the density? Immediately people will say density increases. You know why? Density increases because they think the strength is increasing, so lime should have increased the density. It is not because of the density increasing that lime will improve the strength of the soil. It is because of the flocculation of soil particles and subsequent cementation of these flocculated soil particles by cementitious compounds that are produced by interaction of lime with the soil silica. So it is a drama of soil silica and calcium. I can say lot more about this love story of calcium and silica, not only in soils but in other cementitious materials that are used for construction of various buildings. In fact, I was about to say, Professor Reddy, not necessarily in the geoenvironmental scenario, but the story, love story of silica and lime is a very interesting story, and the material behavior can be very drastically different. That is a big subject by itself. I am not going. But again, this good improvement is seen in the soils by addition of lime is not free from other effects of chemicals that are present in the system. So particularly when there is a sulfate in the soil, and without knowing that, if you try to stabilize the soil with the lime, you are gone bad, worst. And the behavior of lime stabilized sulfatic soil is worse than not stabilized soil. So by stabilization, you are inviting great problems. And of course, all of you know why this these soils can, sulfatic soils swell because of formation of calcium silicate hydrate gel, which is a cementitious compound, is converted into ettringite, which is a swelling type of soil. See, again, I am little bit intrigued and I try to probe little more. Suppose to a soil, if you had ettringite mineral itself, can it swell? But I found not the case. But the ettringite that is formed after interaction of the lime with silica and calcium silicate is formed slowly. These needle-like structures of ettringite are formed, which has got lot of water. When the water is absorbed so high into the interlayer, the particles are separated. There is a huge swelling in soils in the presence of sulfate. So my submission to those who are continuing to work on lime stabilization, particularly in the different environment, this is one case of effect of sulfate. We don't know in future, the way we are contaminating the soil, what type of chemicals will damage the good behavior of stabilized soils need to be foreseen, and appropriate measures should be taken. And It is not that this is the actually learning point for me to probe further the uncharacteristic soil behavior of soils. So I'm watching time also. Normally when I'm involved, I lose track of time. So this sulfate which is formed. So my hunch I will give now itself. If a mineral is converted in the soil, foundation soil, when it is actually acting as a supporting the structure, the formation of one mineral to another is a key to all this unexpected swelling in soil. Say, for example, every paper you read, when there is a heterogate format form, the soil swell. But when I add heterogate mineral to the soil, will it swell? That is a different. So this is the starting or learning point for me to probe little more on the uncharacteristic swell or unexpected or people, including great professors like Mitchell. They say it is surprising. Surprising soil behavior is one paper. It is surprising because you have not anticipated. You don't know the not that we know. We cannot do go on expecting problems from various kinds of things. We are learning from failures or problems that have occurred in the soil mechanics, foundation soil failures because of unexpected behavior. One of them is the conversion of one mineral to another when it is in the foundation subsoil makes a huge difference. That's why all by uncharacteristic soil behavior, whether it occurs the way conventional heave or swell occurs in the soil or it is different. One, I will give another hint now itself as the time is running fast. When the soil is undergoing or mineralogical changes are occurring, the kind of change is doing something much more than what you think. The minerals that are new minerals that are formed are more swelling type. That's why what happens? This interaction more than often, it goes very, very slowly. So initial swelling takes place after a long time. You don't know. If you do the conventional odometer test, if you observe for 24 hours when there is no change, you load it and say it is okay. But sometimes the swelling occurs after very long time. In fact, my student, some of them are here. I'm not mentioning the names of all of them. They waited for 6 months of in a odometer putting some whatever chemicals it is, sulfate or hydroxide or many acid, salt, all these things, the swelling starts after 3 months, after 1 month, after 6 months. So you should have lot of conviction that something is going to happen. So this is the point where I started unconventional swell can occur in the soil when the mineralogical conversions are taking place in the subsoil. So with this submission, I will try to run fast.
No problem, sir. Just take your time.
I'm worried about time because I get involved. So this kind of thing occurred. So this is your heterogate, what people say. Now I will come to a few case studies reported by earlier and my own experience of unexpected soil behavior of weaving. The first I told you, one of the classical clays is in a fertilizer plant where there are draining out the waste treated phosphate. Phosphate is used for the manufacture of fertilizer, and this fertilizer leaks into the subsoil. And slowly, and that soil is a non-swelling kylenetic type of soil. Nobody expected that soil will swell. But as slowly, as good as many years of, many decades afterwards, the soil started swelling, heaving. This is because, and this heaving is much more in kylenetic soil than in monohydratic soil. Because this hydroxide is replaced by bulky phosphate ion, whose structure is similar to water. I am not going to explain the structural similarities of water and phosphate, unlike hydroxide, that will separate the kaolite particles. And this being the case, when phosphate is introduced into a non-swelling soil, that soil swells a lot. So when you put a phosphate in a jar of a weight, to measure the free swell, you can see kaolite swells much more than montmorillonite. If I say kaolite swells more, people won't accept. What is swelling or non-swelling is an environmental related parameter. We cannot say swelling soil, swelling, non-swelling soil in all the environments, particularly phosphate. One of the fertilizer factory, of course, I myself dealt with other case. Then I went to literature that was also reported earlier. Then we wanted to check whether it is really true that when the phosphate comes into the foundation soil, they swell. So what we did is we collected uncontaminated soil nearby fertilizer plant and see the conventional odometer test. When you add water, normal. In the rebound, when you put phosphoric acid, it rebounds more. So these swells. This we have put repeatedly at different pressures and put water or acid. We found always water, it will settle. If you put a water, it will rebound more. Rebound, huge rebounds. That means when you put acid and take out water in the odometer to the extent possible and try to put phosphoric acid, it will swell. So we have confirmed that the soil can swell, will swell in kylenetic soil if phosphate is present. So this is the issue. This is I repeated in some other case. So studied, this is because of replacement hydroxide. Simple, any student can do in a kylenetic soil, put water, some free swell will occur. Instead of water, if you put sodium hydroxide, instead of hydroxide, if you put fluoride, HF, any fluoride, sodium fluoride or something, it will swell more. Because hydroxyl ions has hydrogen bond between interlayers. But when that hydrogen bonding is removed by presence of fluoride, the kylenetic soil will swell. So this swell is again unexpected, surprising swelling in soil. This is surprising because we never thought kyelenite will swell. When it swells, we call it a surprising and close the chapter. But we have to probe and try to find out that can swell. This is similar case reported in a Jordan fertilizer plant, similar thing. And when this is one story of one type of soil, where the type of soil changes, the story varies to different degrees. So each case we can explain for 1 hour, so now we'll talk about remedial measures. Unlike the swelling that is controlled by imposing higher surcharges, this kind of swelling cannot be stopped by increasing the surcharge. So your conventional jacking of the foundations or tilted tanks by other side, of course, you can also go to the extent of connecting to PISA tower. What way you can use this method to control the leaning of the PISA tower. And of course, that is much more sensitive. You cannot do any experiment on that. But the conventional methods of correcting the tilting of the buildings or tanks or towers is not possible by conventional understanding in geotechnical industry. Another thing, little bit more, is that when caustic soda enters the soil, there will be, they observed the foundation heaving after 20 years of operation. Of course, I am fortunate to have one connection with one industry where they approached me for this correction. After trying all their conventional methods of controlling, they try to leach out, they try to load, all methods of conventional methods of correcting the damage to the floors. And this damage is much more in the light structure than heavier structure. So the floors started heaving, and when after about 30 years, they found about 2 feet of swell in the foundation, the whole building. And that is only a shed, but it has not collapsed, but it is settling or heaving more. But again, differential heaving, whether we talk about uniform or differential heaving. Luckily, the tilt is difference is not very high, so the structure survived. And of course, subsequently, we suggested remedial measure for correcting the rising of the floor due to alkali contamination. So now, coming to the mechanism of correction to heave caused by sodium hydroxide or alkali solutions. I will give one case study, little more, maybe 5 minutes. I will try to wind up. Under 5 minutes, sir, 10 minutes, Professor Reddy?
Yeah, no problem. Go ahead.
See, this is one case, in one company where they are processing bauxite ore. Bauxite ore is very stable. To extract alumina, it has to be digested at very high temperatures and pressures with a strong alkali solution. So when there is a treatment of this bauxite with alkali, very strong alkali at high temperatures and pressures, leakage occurred. That's why I say, in fact, next slide, you see how the alkali is leaking into the foundations of the factory. Alkali is spread into the foundation soil. So you can, normal problems of concrete is one thing, that aspect I am not covering today. But into the foundation, when it goes, lot of damage is done. See, that's why I say, it is not the problem of civil engineers, it is the poor mechanical engineers which allowed leakage and converted all geotechnical engineers into geoenvironmental engineers. So this soil is heaving because of alkali. But this heaving, unlike in some of the cases where I have presented, it is that not only kylenetic soil, montmagnetic soil also can swell. This is the case where swelling can occur in any type of soil if it interacts with the alkali solution. Of course, one answer is geolization of the minerals by interacting with the alkali. So these are, we call that modified. In fact, now I try to say it is modified. India is getting modified now, not modified. It is, so the soils also can get modified, and lot of this occurs for any type of soil, whether kylenetic soil. Now, how do you prove that kyanate can swell? And what is the effect of duration? What is the effect of concentration? So we have studied one soil, compacted to the same density, and allowed conventional odometer test with water. And that is, instead of water, we have used sodium hydroxide of 1 normal and 4 normal. And then under third series, where the soil itself is initially compacted not with water, but directly with sodium hydroxide, and then added further sodium hydroxide. So we have studied the effect of first occurrence of contamination of varying concentration, and then whether whether if the soil is already heavily treated with alkali and then put the foundation, then the soil will not swell much. So in this process, but somebody was asking, when I was trying to present to one of the prestigious institutions in India, they asked, that is not the standard procedure. We have to use only 24 hours and say whether it is swelling or not. And you have to say, this soil has liquid limit of only 50, how do you say it is swelling? So all this is nonsense. So this kind of a thing. But we have to do elaborate and years and hours of time to do consolidation test. I think some of my students, Arprasad Reddy, Shankara, Manju, so many people have worked on this, approved, whether it is concentration, time effect, person effect, equipment problem, change equipment, change the person, whether do in the night or daytime, temperature effect. So a lot of variables we have to incorporate into the testing procedure, not 24 hours, sometimes months and months we have put. See, sometimes what we found is, I'll tell you one classical case, where you put the soil, you treat with the soil with alkali, do the normal 24 hours loading, duration of loading is keep 24 hours, and then we unload. There is during unload, there is a huge rebound. Sometimes it crosses the initial void ratio. After loading and unloading, which took longer time, the final void ratio was more than the initial void ratio. Normally, if we do that in undergraduate, the teacher will blast you on throat. How can be the final void ratio more than the initial void ratio after the consolidation test? So likewise, but we have proved many times that rebounds will be much more if the soil is contaminated, because by the time you complete the loading cycle and then start unloading cycle, the initial reaction, the conversion of the minerals into something else. And of course, we have studied what mineral can convert into what mineral. And this is the one cell. See the initial void ratio, this one, and then it goes very steep. Can you show this to any? If you do normally, you don't find, but if you do little time, then load it, unload it, it goes very steep. This, if to report this kind of results, we need a lot of conversion and repetition, number of times to show that the soil starts swelling during rebound. That's why next stage of test is we allow the reaction to complete in the nominal load itself, say for 1 month, 2 months, then it behaves normally. So once the reaction is over, the behavior is different. During the reaction, the behavior is different. What I am trying to highlight, of course, concentration plays a role, the type of minerals plays a role, but the soil, if it is initially itself is contaminated with the fluid that it is going to interact in its lifetime, the behavior is okay. That's why we say, if at the age of old age, when you have seen everything, you don't care for anything. You have achieved mature level, the soil will become mature. If it is allowed to interact with the highest concentration, that is likely to come subsequently on this kind of soil. This occurs for almost all type of soil. So we found many soils, rebound is much more. Of course, we have studied the effect of, one of the effect is geolitization, which is highly swelling. And see, one maybe I'll try to wind up another 5 minutes. You see, both red earth and red earth, at a nominal surcharge, we kept it for 1 month. For 1 month, no swelling. Simply no change in dial gauge reading. But once it starts very steep. Even with the lowest concentration of 1 normal, and soil compacted with water, and then replace or inundate the soil with sodium hydroxide, it will swell. A kinetic soil swelling up to 14% is unimaginable. And this characteristic swelling, which initiated almost after a month, cannot follow your hyperbola relationship. This curve is different. Initially for long it will no change at all. But change occurs, it changes phenomenally. So the swelling is unexpected. This is because of conversion of these minerals into something. Again, if I compact the soil initially with the sodium hydroxide, again the swelling will be less. So this is soil. If you put instead of 1 normal, again 4 normal for a non-swelling soil, it can further increase too much. But not only the amount of swell increase, the initial swelling point also decreases. As the concentration is higher, the concentration, the swelling starts within 10-15 days. Whereas in the case of 1 normal, it took 30 days. If it is 4 normal, it takes only 15 days. So this is the kind of interaction. But in the field condition, the continuous swelling occurs because as the leakage continues to go deeper, fresh soil is available for interaction and conversion. So it never gets matured very quickly. It takes very, very long time to the soil to become don't care for contaminants. Similarly, can it happen only for kyanite? No, it can occur for montmorillitic soils also. See how one soil, the normal swelling, what you call swelling soil of black cotton soil, we call it in India, montmorillitic soil, it is only about 2.5% swell. But the same soil swells about 18% with 1 normal. And it can swell up to 25% with 4 normal. So this is the kind of changes that can occur with the contaminant. Again, similarly, what is the effect of this swelling on further consolidation behavior we have studied? And see how all this rebounds crossing to the initial point or more can occur. And interestingly, we have done sufficient number of soils, sufficient concentration, time, duration, persons also varied to see that whether any fellow is doing any trick or any fellow doing any mischief in the laboratory. So all those points. Then how to control? How to control this kind of swell, whether you should use ferric chloride as conventionally somebody told in earlier cases. But we have tried various other options. I think that is a big story of controlling the swelling of induced swelling, what I used to call uncharacteristic, unexpected, surprising swelling in soils using fly ash, etc. And potassium chloride, because potassium can link the montmorillitic soil and causes some bonding by linkage of potassium, like in the case of illitic structure and other soil. Whether all this story is only restricted to alkali? No. It is alkali can swell both kyanite and montmorillite. Similarly, I have studied acids, where another case where sulfuric acid can make the soil to swell. This is the swell, you see. Again, I have seen it can swell by 50%. This is unimaginable. Likewise, of course, what are the mineralogical changes? Whether it can occur for swelling, for non-swelling soil also. See 1 normal and 4 normal. You see, 1 normal can swell up to 18%. 4 normal can increase the swelling by 60% in non-expansive soil. But when 1 normal takes about 150 days to start the swelling, and we have to fight for the consolidometer. If you block it for 6 months, all people, those days, a lot of experiments are going on, and there is a fight for consolidometer. Simply keeping the consolidometer for one fellow starts, so 1 normal, it starts only after 150 days. Whereas 4 normal can initiate about 75 days. So can you simply keep and wait, praying for God for the soil to swell or sink? But it needs a lot of conviction and then, of course, we have taken out the soil, we have studied all its changes and what are the mineralogical changes. Whether the story of I'm winding up 2 minutes. Soil due to increased salt also can be there. I worked on a case where salt Infiltration into the foundation soil can also swell. Another thing, this is the thing, what are the mineralogical changes that occur in different kind of soils, in different environment? What are the new minerals identified? This conversion of one mineral to other is mainly responsible for this kind of unexpected heave in soil. So this now, all this, what are the things can occur? We can go on. This is the energy changes associated with the mineralogical transformations of soils, the presence of various contaminants, and of course, what can occur. What is the characteristic of conventional soil, conventional fluid, and in a contaminated fluid? So what can occur? So I summarized in table. And don't think all is positive, all is negative. You can also help us in some cases. It can form informal soil layer. So instead of creating a soil liner, constructing, you can modify the soil by using appropriate chemical into impermeable system. So this is the story where people say there is a bridge between India and Sri Lanka, that what you call Adam Bridge or Ramasetu is also by some trick of converting into the rising soil. So these are some of the conclusions where the Ramasetu. Now, another issue is we are struggling to cope up with the problems of behavior of soil in a contaminated ground. But now we have landed on moon, and what kind of soil, what kind of problems will occur in future, we have to be prepared to study the changes on the type of earth on the moon. I think this is what I wanted to convey quickly about the unexpected heave in soil and the consequence and remedial measures. Each one is different. I'm not going to think. I thank once again Professor Krishna Reddy and all the participants for listening to me. I think my time is up. I think more than up. Okay.
Thank you.
Thank you very much, sir. Thanks you everyone for patiently listening.
Yeah, thank you. Thank you so much, sir. I think it was a wonderful presentation. I think we had more than 200 people. Now we have 160 people. So patiently they were listening, and it's so interesting. I think a lot of geotechs have to
So our audience
look into the soil minerals and the effect of ionic concentration and chemicals, and looking at the long-term effects. So I think I see a lot of comments in the chat box, and they're all very appreciative of what you presented. I think that's I say that geoenvironmental engineering is basically a combination of geotech and looking more into the details of chemical effects. So it's a very nice presentation, and hopefully it has given a lot of ideas for people to investigate some of the complicated things that you suggested. I mean, I started my research. I did exactly the same experiments that were done on kaolin by many researchers. I just took a soil from Chicago area, and I did the same experiments. So same experiments that a lot of people have done on kaolinite, and everybody was able to duplicate the results. But then I said, okay, we want to apply this one in the field, right? So I got a field sample. I did exactly the same experiment. I found totally different results, and it's all due to the changes in the differences in the chemical composition and ionic strength, and all those things. So we don't want to play around with just ideal minerals. You pointed out that mixed minerals could be much more complicated, and also the notion of swelling only for montmorillonite may not be correct. So you have pointed out very clearly that non-montmorillonite minerals also can swell. That needs to be looked into. I think it's very enlightening. I don't know if you want to answer questions in the chat box, but that questions can be shared. But I would suggest everyone to open your video, and then maybe you can ask some questions. I have questions in the chat box. Definitely, I'm going to copy these questions and pass on to Professor Sivapullaiah. But I think since we are on online,